Welcome everyone. My name is Arpad Forberger and I'm an application engineer at Gamax Laboratory Solutions Ltd. Today we are going to take a look at the basics of how COMSOL is used for modeling hyperelastic and other nonlinear materials. I will walk us through some models to give you a chance to see the software up and close and see how it might help you in your work. If you have never used COMSOL before and you want to learn how it works, my presentation today should help answer those questions. And today's agenda look like with a short overview of the model setups, and then we can see the model definition itself, and then during the live demonstration I will set up the problem from scratch and show how you can modify boundary conditions and mesh settings, how to analyze and post-process results. At the very end I will mention some further resources where you can find more information, including full-length webinars that contain more technical detail than what we will have time for today. Today's presentation is really meant to be a quick intro to see what the software is, but we have many resources available, and if you are interested in learning more, you are more than welcome. And if you find this webinar presentation a bit fast, don't be worried, because we are recording this so you can see the recorded webinar, so we will share you the link in the follow-up email, and feel free to type your questions in the chat window. I try to answer those here in the webinar or after the follow-up. So COMSOL Multiphysics is a simulation and application design environment where all of the steps of a simulation are integrated into one user interface, from the initial setup to the solvers to post-processing to putting together a custom-built application. A COMSOL model allows you to couple together physical effects the way they are in the real world, which we refer to as multiphysics. The model we will look at today solves for the deformations and strains of a car door seal using nonlinear material models. Once you have completed your COMSOL simulation, the software allows you to create a customized app from the model, which enables you to deploy the analysis capabilities and results to collaborators, customers, or even colleagues around the world. This is our product suite, so we have add-on products that can be combined with the COMSOL Multiphysics core package to enable simulation of specific physics phenomena across a range of application areas. These can all be combined with each other. We have modules for electrical, fluid, heat, mechanical, acoustics, and chemical simulations, as well as several multi-purpose modules and tools for interfacing with external software, with various CAD programs and MATLAB itself. Include functionality from the modules of the structural mechanics and the nonlinear structural materials module. We have several different components to the COMSOL software. Right now we are looking at the model builder in the COMSOL desktop, which you will see live in a few minutes. The model builder contains the tools for controlling physics, mesh, materials, and study settings. Because, as I mentioned earlier, once you are finished with a simulation, you may want to be able to share the results with a colleague or a customer without sharing your entire model. The application builder will let you build this user interface around your simulation. Then, to share it with someone who doesn't have COMSOL installed on their machine, you would use a local installation of the COMSOL Server, which makes the app accessible either through a COMSOL client or a web browser. What's really powerful about this is that the person you share the application with doesn't actually need to have a background in COMSOL numerical simulation, which makes the app accessible either through a COMSOL client or web browser. Okay, and today's model will include this hyper-elastic material model included in this door seal. So we will have three different domains in our computational domain, in our geometry. So here the upper part is considered to be a rigid domain, so this will move in the -y direction to compress this black seal, so it's made of rubber, and we will have another L-shaped part that can be considered as a part of the car frame. So we will close the gap between the door, which can be considered the upper part, to the fixed L-shaped domain. So those are rigid domains, and the inner part, which is the rubber, it's a hyperelastic material model with a two-parameter Mooney-Rivlin material model. So it's a highly nonlinear, so we have contact surfaces between the L-shaped fixed boundary and the moving upper boundary, and the material model is also nonlinear, and we can include friction in the contact domains. And also we can consider the inner pressure, so we can include that one as a boundary load. So we can consider it's an adiabatic compression, so the contained air inside the seal, and from reorganizing the equation, the pressure increase can be calculated, as you can see in the second equation. And we can set up these variables and equation in COMSOL Multiphysics quite easily. So now I look into the model itself, so I jump into COMSOL Multiphysics. So first, since it's a 2D geometry, I will choose a two-dimensional domain. Then from the physics branches, I go to structural mechanics and select solid mechanics. And after you have selected the physics domain, you can select what kind of study you would like to solve. For solid mechanics analysis, these are the available study settings, so we go for a stationary solver. To speed up the computation, I will import the geometry sequence and also some variables. Okay, so this is the upper part, so this will move down in the -y direction to compress this seal. It's made of rubber, and we have this fixed steel part, which can be considered, as I mentioned earlier, part of the car frame. From the definitions, we will add some variables. I will open up, because I already created them, and here you can see this is the int p, the internal pressure that can be used as a boundary load. So for this we need to calculate the area of the seal, because it's changing during the simulation, so we will set up a variable for this one. So we need to calculate the area of the seal, so it's quite easy to do that. In the follow-up email you will see how it's done. So now I set up an integration operator to calculate properly the area that is changing over the simulation. Okay, and this is the area int. Okay, so this is an integration operator. So whatever you put into the suffix, into the parentheses of this operator, it will integrate over these boundaries. So if we go back to variables, you can see that we integrate the x coordinate dot the normal component of the x coordinate. So this will give you the enclosed area at every time instant during the simulation. And this is how the internal pressure will look like. So it's from the second equation from the previous slide. Okay, to set up contact problems, we need to set up two contact pairs, one for the upper moving part and the outer part of the seal. So the source should be, we can simply select these edges. So these are the source boundaries. And for the destination we have the outer edges of our seal, so they will be in contact. Okay, so that's for the first contact pair, and we need to do the same for the lower part. Pairs, contact pairs. The source is from 1 to 6, which means the fixed L-shaped part, so that will be the source boundary for the second contact pair, and the destination is the same, the outer edges of the seal, so they will be in contact during the simulation. So we have two contact pairs, one for the upper moving rigid part and the seal, and one for the seal and the lower fixed part. For material side, we will add the structural steel for both materials. So we go to built-in materials, structural steel, and simple deselect the seal itself, because we will define our own material properties. And here all the properties are set up correctly. Okay, and we will set up the material properties for the seal later in the physics domain. So if we go to the physics interface, we can add hyperelastic material, because this is made of rubber. Simply select the domain and select monirivlin 2 parameter, and we will set up manually these parameters. So this C10 is 0.37 megapascals. You can use the square brackets to indicate the unit. For C01 we will use 0.11 megapascals. Initial bulk modulus, so we set up a fixed constraint here. It's 1 to the power of 4 megapascals. Okay, and the density, let's say it's 1100 kilogram per cubic meters. Okay, so these are the material properties for the model. So we need to add a fixed constraint, because this frame is considered to be fixed. We need to add the moving domain constraint to the upper part, because this part will move in the minus y direction. Constrain the displacement in the x direction to 0, and this is the minus para times 1 millimeter, so we need a parameter that will change over time. So we go up and put a parameter here. Okay, start it with 0. Okay, so the upper part is moving down with a parameter. We have a fixed boundary, we have a nonlinear material model, and we need some pairs, some contact pairs. So we already defined these contact pairs. One little thing is missing. We need to add the friction coefficient, consider it 0.2. And to make the model more rigid and robust, we consider that the seal is glued together to the fixed domain. So we need to add the spring constraint here, spring foundation here. So we consider they are glued together, and we can set up some value for the spring coefficients, 1e10 and 2 to the power of 10. Okay, so that's from the physics node. From the mesh node, we look into the physics-induced sequence, and we set up some manual sizing. So we restrict the size over this domain, over the upper domain, to 0.4 millimeters. We restrict the size of the seal to 0.8 millimeters, and we set up manually the size limits over the outer boundaries, because these are the contact boundaries and they are elastic, not rigid, so we need to limit the size manually. It's safer for convergence problems. 0.15 millimeters. Okay, so that's the custom built mesh settings. Okay, and for the solid mechanics interface, one little thing is missing, that the boundary load, so the internal pressure here. So we will consider the internal pressure. As the boundary goes down, the inner pressure increases, and it was int p, int underscore p, that was the variable. So that's from the physics. To speed up, I will open up the solved model and we will look into the results, how they look like. And here we have two study steps, one without the pressure. So in COMSOL Multiphysics you can simply disable boundaries like a boundary load. So you simply click in modify physics tree and simply click on a boundary and you can enable or disable, it's up to you. And we have a parameter, as I set up earlier, that goes from 0 to 4 millimeters. So it means that this upper device will go down to 4 millimeters. And for the second steady node, we don't have any modifications, so we will include the internal pressure here as well. So it's a simple stationary solver with two contact pairs included with a hyperelastic material model. So we can look into the model. So this is the mechanical stress, the Fomise stress for different parameter sets. At the final step where we have 4 millimeters displacement, and we can select any initial step to look into the model how the stress changes, or we can see how the contact pressure is changing over the boundaries when no internal pressure. Okay, so we can go to the second step. This is true for when we include the internal pressure calculation, so we will have higher values. And of course we can compare the two studies, that's more interesting. So how much force do we need to compress the seal, whether you include the internal pressure or not. So here you can see the upper, the green line corresponds when you have the internal pressure, and the lower blue curve indicates the force required to compress the seal when no internal pressure is considered. And of course you can simply, if you would like, you can go to create an animation quite easily here. So you can include all your solutions and you can loop it and you can export it to any presentations if you would like to see this. So this is one little example of how to define hyperelastic material models, but there are also other material models, not just this one. So you can have several other models that you would like to use. These are the predefined interfaces for them, and as always you can use a user-defined, so you can include your own material model quite easily. And the second example I would like to show you in a few seconds is so-called die forming. So we have a very thin sheet and we have these upper fixed forms, devices, and in two stages. First, the lower part, this lower L-shaped part, will move up and to bend our little plate. And then in the second stage it goes like this, that the lower inner part goes down, and in the third stage all these moving parts release and our plate is ready for forming, and that's the final stage. And if we go into the model itself and we play the animation, you will see the step-by-step moving of the die forming, and you can plot quite easily how the thickness is changing during the three different stages. So I just want to show you the animation itself, and in the follow-up email you will get the full documentation and all the steps, so you can reproduce quite easily. So here you will see all the three stages of this movement of this little sheet, and the color is changing according to the plastic strain, and of course we can change the coloring according to the thickness, how the thickness is changing during the die forming. Okay, so this is stage one. The lower part moves up and forms a shape. Then in the second stage the smaller part will move down to bend on the left side. And after this one, the third stage is coming, so when the plate is released and the final product is ready. So that's the third stage that's coming here. Okay, and if you want, you can select the thickness, and we can look into how the thickness is changing during the 3 stages. Okay, so this is how die forming works in COMSOL Multiphysics. And if you need more information, you can go to our website. As soon as the movie is being generated, I switch to this one, so you can visit our website or you can write us directly. You can access, you can ask for a free trial version, so if you would like to try out the capabilities of the software, it's more than welcome to write us, to reach us, to contact us, and you can find lots of videos and webinars and lots of models at the website. There are more than 600 models. You can freely access them, all the documentations and all the models itself. So there are much more than we could show you here in this little webinar. Okay, so if we look into the thickness, you will see how the final thickness, how the plate behaves during this kind of die forming. Okay, so the initial thickness was 0.2, and as the result of this die forming process, as a result of these 3 stages, some portions below thinner, like 0.16 millimeters, and some portions of the plate become thicker, like 0.22 millimeters. So before releasing this device, before the manufacturing process starts, you can create some kind of simulations and you can see the effect of the curvatures and other phenomena in this die forming or deep drawing example. So now I wrap up my demonstration, so if you need more information, feel free to reach us, and you will get all the slides and presentation materials in the follow-up email. Now I thank you for your time and see you in our next webinar.